Here's the video to guide you through the scalar product investigation. For number one, it gives us two pairs of vectors that might be perpendicular, might be parallel in two dimensions. And so the first pair we have here, 3i plus 2j and 4i minus 6j, it asks us, what are ways you can figure out that these are parallel, perpendicular, or neither? And since these are two-dimensional vectors and we have a grid here, we could graph them, right? So I'm going to graph 3i plus 2j, and I'm going to graph 4i minus 6j, and we're going to compare them and see if they might be parallel or perpendicular. So 3i minus 2j would be 3 in this direction and 2 in this direction, so that would be this vector here. And then the 4i minus 6j vector is going to be 4 in this direction and minus 6 down. Okay, and so that would be, that would be that vector. Okay, and so these appear to be perpendicular. Okay, and how can we be sure that they're perpendicular? Well, recall that the slope of a line and the slope of a perpendicular line have this relationship. Okay, so one is the negative inverse of the other. Okay, so let's take the slope of this. The slope of 3i plus 2j is going to be 2/3. Okay, and the slope of 4i minus 6j is going to be negative 6/4, which is actually equal to negative 3/2. So now we've just confirmed that m and negative 1m relationship is maintained here. So do you see how this is m and this is negative 1/m? This is the negative inverse. So we've confirmed that the slope of one is the negative inverse of the slope of the other. So we have confirmed that these two vectors are indeed perpendicular. So these are perpendicular. Okay. Then we're going to go down here. Now we have 5i plus 2j. So that would be this one. Okay, so it's kind of like that. And then we're going to do this one, which is negative 2i minus 5j. So negative 2i minus 5j. 1, 2, 3, 4, 5. So it's like that. Okay, and no, these are not perpendicular and they're not parallel. Not perpendicular, not parallel. Okay? All right, moving on. Number two, they give us two 3D vectors, and they're asking us, is this vector pair parallel, perpendicular, or neither? What are ways you can find the answer? What are the answers? Okay, so looking at these two, we notice that there's a pattern here, 2, 2, 2, and this one has 1, 1, something. Okay, now if this was 2, 2, 2, and if the other one was 1, 1, 1, then we do know that these are in the exact same direction, right? Because if we ever have a vector and another vector, and they can be related by multiplying a scalar, which is true in this case, okay? Then we know that they're in the same direction, or that they're parallel. They might not be in the same direction because they might be in the opposite direction. Okay, but in this case, you can see that if it was 2, 2, 2 and 1, 1, 1, then we would know that they were not only parallel but also in the same direction. But the last number, instead of being +1, which would have made it perfect, is negative 2. So we know that they are not parallel. Okay. If it was parallel, then it would be 1, 1, 1. If you change one of the numbers, then you've ruined it. It's not parallel anymore. Okay. Now, is it perpendicular? Really hard to tell. Okay. Now let's have another another example here. Here we have 1, 1, 2 and 1, 3, negative 2. These are two 3D vectors. And here it says we can figure out maybe if that they are parallel or perpendicular by doing the same method that we used in the problem set that we've done recently, where we proved that 3 points of a triangle are perpendicular. So you might say, well, we don't have 3 points here, we have 2 points. Well, actually, one of the points is the origin. Okay, so basically we've got 3 points. We got 0, 0, 0, which is the origin. We got 1, 1, 2, which is that vector here, that position vector. And we have 1, 3, negative 2. Okay, and so we're going to compare the triangle that is formed by these 3 points. We're going to compare the sides and see if the sides form a right triangle. And if they do, then maybe they're perpendicular. Okay, so let's see. We'll label this one A, this one B, and this one C. And so first we'll say AB. AB, we know, is the vector 1, 1, 2. We know that BC can be, we're going to do C minus B. So 1 minus 1 is 0. 3 minus 1 is 2, and negative 2 minus 2 is negative 4, so that's BC. And then finally, we have AC, which is 1, 3, negative 2. Okay? And then we just need to find the lengths of each one of these. So the length of vector AB is equal to 1 squared plus 1 squared plus 2 squared, which is 1 plus 1 plus 4, which is the square root of 6. Then the length of BC is going to be 0 squared plus 2 squared plus negative 4 squared, which is going to be 16 plus 4 square root, which is 20. And then finally we have one side, which is AC. And this one is going to be 1 squared plus 3 squared plus negative 2 squared, which is 1 plus 9 plus 4, which is going to be 14. Okay? So we got 3 sides, 1 square root of 6, 1 square root of 14, 1 square root of 20. We're going to see if they obey Pythagorean's theorem. If they do, we know it's a right triangle, and if we know it's a right triangle, that means we know that the two vectors are perpendicular. Okay? So we're going to put square root of 6 squared plus square root of 14 squared equals square root of 20 squared. How did we know that we're supposed to put square root of 20 by itself on the right side? Because square root of 20 is the longest side, so obviously it would be the hypotenuse if there is a hypotenuse. And we can see here that actually we have found a right angle because 6 plus 14 does equal 20. Okay, so that means that that this vector AB and this vector BC are indeed perpendicular to each other. Okay, so it is perpendicular. Okay. Okay, now we're going to get to the section of the investigation, which is based on the movie Castaway. If you remember when the Tom Hanks character Chuck saved himself, he was lucky enough to have his raft cross some shipping lanes, and a container ship saw him and rescued him. So let's say that Chuck was actually going to make a plan to actually go with his raft and try to meet the shipping lane. Okay, so we are going to draw that as vectors, and we're going to see exactly in which direction he should go. Okay, so the first step here is to choose a 2D position vector for Chuck and write the vector here. So let's say, and you can choose any vector. I'm going to choose a vector like 3, 1. Okay, so that's the position vector for Chuck. And then I'm going to write a position vector for the ship, and I'm going to put something like 2, 8. Okay, and then it says to choose a 2D velocity vector for the shipping lane, and to write the vector here, choose a vector that does not have components equal to 0. So I'm going to say 2, -1. Okay, And then it says to mark the positions on graph paper and draw the shipping lane below. Okay, so first I'm going to draw Chuck, which is at 3, 1. So that's Chuck. I'm going to mark it C. Then I'm going to draw the ship, which is at 2, 8. 2, 8. There's the ship. I'm going to draw it at S. And then I'm going to draw the velocity vector for the ship, and it's going to be 2, -1. So 2, -1. So this is the shipping lane velocity vector. Okay, and then so how does the velocity vector, or how does the shipping lane look? Well, if you extend the velocity vector from here, then you can see that basically it looks like that. Okay, and then it says to draw a displacement vector, which is the shortest path between Chuck and the shipping lane. Describe the relationship between the displacement vector and the shipping lane. Okay, so if you have a line like the shipping lane and you have a point like Chuck, then the shortest line which connects C to the shipping lane would be a perpendicular line. Okay, and remember that the perpendicular line has a negative inverse slope as compared to the shipping lane line. Okay, so here we've drawn the displacement vector that would take Chuck to the shipping lane, and we also know that the displacement vector and the shipping lane are perpendicular. Okay? All right. Now we're going to move on. We're going to come back to Castaway at the very end of the investigation. So we're going to draw a short vector and a second vector that's parallel to it. Okay, and so I'm going to draw a vector here that is 2, 1. Okay, and then I'm going to draw another vector which is parallel to it, but maybe a different length. Okay, so there's this vector and there's this vector. Okay. Now I'm going to draw a short vector and a second one that's perpendicular to it. Okay, so I'm going to draw one vector that is 3, 1, and then I'm going to draw another vector that is 1, -3. Except I'm going to make it twice as big. Okay, so now I'm going to write down the components of the vectors. So this one here is 3, 1, right? And the blue one is 2, -6. And these parallel ones here, one of them is 2, 1, and the other one is 4, 2. Okay. Number 5. Calculate the lengths of your vectors in case 1 and multiply them together, and do this in case 2 also. Okay, so for case 1, I'm going to multiply the lengths of these two vectors. So what's the length of the vector 2, 1? Well, you find this length by using Pythagorean's theorem. So you could take the square root of 2 squared plus 1 squared, which is equal to the square root of 5, right? What about the length of the vector 4, 2? So that would be, Pythagorean's theorem would give you 4 squared plus 2 squared, which is 16 plus 4, which is 20, would be square root of 20. Okay? So the shorter vector has a length of square root of 5. The longer vector has a length of square root of 20. And if we want to multiply those together, which it says here to multiply them together, we don't know why we're supposed to multiply them together yet. But square root of 5 times square root of 20 is actually equal to the square root of 100, which is actually equal to 10. Okay? Now let's do the red and the blue vector here. So the length of the vector 3, 1 is 3 squared plus 1 squared, which is 9 plus 1, which is square root of 10. And then the length of the blue vector here is 2 squared plus -6 squared, which is 36. So it would be square root of 40, right? And if we multiply these two together, square root of 10 times square root of 40 is equal to the square root of 400, and the square root of 400 is equal to 20, right? Okay. So now we're going to move on to 6. It says, And then we're going to start to understand why we multiply these together, as finally when we get to number 7. Express your vectors as vector v and vector w in component form and multiply them together in the following manner called the scalar product, dot product, or inner product. And so we've expressed the two parallel vectors as component vectors here, and we're going to multiply them together as a scalar product. And you don't know what that means yet, but it's a pretty easy process. Understanding what it means is a little bit harder, but the process of doing a scalar product is pretty easy. The way you do it is you're going to multiply the 2 times the 4, and you're going to multiply the 1 times the 2, which seems kind of a logical thing to do. And then you actually add them. You add the sums, you add the product. So it's 2 times 4 is 8, plus 1 times 2 is 2, so actually that gives you 10, right? And that's for case 1, okay? And then for case 2, we're going to take the vectors 3, 1, which is the red vector, and we're going to take the vector 2, negative 6, which is the blue vector, and we're going to dot product those together, scalar product those together. And how do we do that? We're going to multiply 2 times 3, and we're going to add that to 1 times negative 6, which is negative 6. And 2 times 3 is 6, minus 6 is 0. We get 0. Okay? Then we're going to go down to number 7. We're going to finally figure out why we did the multiplying here. So case 1. For case 1, first it wants us to get the lengths multiplied together from number 5. And it was 10, right? So we're going to put 10 here. Then it says the angle between the two vectors and the cosine of that angle. So the angle between the two vectors, since they're both parallel, is going to be 0 degrees. And the cosine of 0 degrees is equal to 1. Now, the scalar product, v dot w, from 6 is 10. Okay. Now we're going to do case 2. So case 2, from number 5, we're going to grab the multiplied length. It's going to be 20. So I'm going to put 20 here. And then we're going to put that the angle between the two vectors, which are perpendicular, is 90 degrees. And then the cosine of 90 degrees is equal to 0. And then we're going to put the scalar product. The scalar product is 0. Okay? Then it's going to ask us, for each of the two cases, case 1 and case 2, is this equation obeyed? So we're going to say, okay, so this part, the scalar product, is the third row, okay? And the magnitudes multiplied together is the first row, okay? And then the cosine is this row, okay? So basically what we're saying is the third row is equal to the first row times the second row. It's true. What about for case 2? The third row is equal to the first row times the second row. It's true also. Okay? So actually, this definition of the scalar product, that it's the two magnitudes multiplied together times the angle between the two, the cosine of the angle between the two, is true. Okay? All right, moving on to 8. Compared to your method on the first page, why is a scalar product considered a more convenient way of finding out if vectors are parallel or perpendicular? Okay, so do you see here that the scalar product is actually a very easy test to see if two vectors in component form are parallel or perpendicular? Because all you need to do is multiply the x components together, the y components together, the z components together, and you add them all up. That gives you the scalar product. Guess what the scalar product is if the cosine between the two, if the angle between the two vectors is 90 degrees or perpendicular? It's always 0. Okay? So that's pretty cool with, third grade arithmetic with multiplication and addition. We can easily figure out if 3-dimensional vectors, 4-dimensional vectors, 5-dimensional vectors, any dimensional vectors are perpendicular or not. Okay? And with a little bit more work, we can figure out if they are parallel. Okay? But perpendicular is quite easy. All we need to do is multiply the x components, the y components, z components together, add them all up. If we get 0, that means that they are perpendicular. And if you go back to your first page, you can actually see that at work. Do you see how, like, if we took the x components here and the y components here, we multiplied them together and added them, we're going to get 3 times 4, which is 12, plus 2 times negative 6, which is negative 12. Look at that. We got 0. So, and we by drawing these out, we figured out that these two vectors were perpendicular. We used the test to see if the slopes were negative inverses of each other, but that was pretty complicated compared to just multiplying 3 times 4 and multiplying 2 times negative 6 and making sure that they added up to 0, right? It's much easier to do the scalar product to see if they're perpendicular than to do any other form, even for two-dimensional vectors. And with three-dimensional vectors, forget it, right? Look how complicated it was to figure out if we had two vectors that were perpendicular to each other using the method of finding the sides for this triangle and seeing if it was the right triangle. That was a lot of work, right? Actually, we could just multiply the x components, the y components, and the z components and add them up and see if they get 0. 1 times 1 is 1. 1 times 3 is 3. 2 times negative 2 is negative 4. Oh my gosh, look at that. It adds up to 0. So we know that these two vectors were perpendicular. Okay? Finally, what about this one? We said that these two vectors here were not parallel, but we weren't sure if they're perpendicular or not. How can we see if they're perpendicular? We multiply the x's together, we multiply the y's together, we multiply the z's together. What do we get? 1 times 2 is 2. 1 times 2 is 2. Negative 2 times 2 is negative 4. Hey, look, it adds up to 0, which means that this set of vectors is also perpendicular. Okay? All right, so now we've checked almost all the sets of vectors here. Now that just leaves Chuck. Okay? So let's figure out if the vector we drew here is perpendicular to the red vector. So we'll see if the blue vector is perpendicular to the red vector. So in order to do that, we're going to say, okay, the red vector is, what's the red vector? The red vector is the velocity vector of the ship, which is this 2, negative 1. So we're going to make sure that 2, negative 1 is perpendicular to this Chuck's vector. And so let's define Chuck's vector. Chuck's vector would be 2 this way and 4 this way. So Chuck's displacement vector is going to be something like 2, 4. Okay? Let's see if the 2, 4 vector is perpendicular to the 2, negative 1 vector. How are we going to do that? We're going to do the scalar product, which we signify with a dot there. We multiply the x's together, we multiply the y's together. We're going to get 2 times 2 is minus 1 times 4, and that's going to equal 4 minus 4. And guess what? That's equal to 0. So yes, we have confirmed that the blue vector that we've drawn, that we've sketched here, is indeed perpendicular to the shipping lane vector, which is in red. Okay, how did we do that? We took the shipping lane vector, which is 2, negative 1, and we did a dot product or a scalar product with 2, 4, which is the Chuck displacement vector, and we found that the scalar product was 0, which means that they are perpendicular. Okay, so now we're going to answer the question on the last page, number 9. Use a scalar product to show that the displacement vector you drew for Chuck is perpendicular to the shipping lane. So we had 2, negative 1, and we had was it 2, 4? And so this was the Chuck displacement vector, this was the shipping lane vector, and by doing the scalar product we found indeed that they are perpendicular because the scalar product was 0. Okay, so scalar product equals 0 means they are perpendicular. And that's it.